Okay, this is discussion 4.2 for IB Chem 1 about phase changes and intermolecular forces. So, in order to talk about intermolecular forces, which are the forces between molecules, first we have to look a little more closely at the molecule and figure out its polarity. So we're first going to talk about the polarity of bonds, then the polarity of the entire molecule. So, all covalent bonds are not created equal. We have two types of covalent bonds, polar and nonpolar. We are going to use electronegativity difference between atoms to determine what type of bond we have. Now, comparing these, nonpolar covalent bonds have an electronegativity difference of 0. Polar covalent bonds have an electronegativity difference of greater than 0. Now, you might be wondering how this compares to ionic bonds, but to differentiate between ionic and polar bonds, we would usually look at the types of atoms involved. So remember that ionic compounds have a metal and a nonmetal. Now, if two atoms have the same electronegativity, they have 0 difference, they would share electrons evenly. In a polar bond, electrons would be shared unevenly, and the more electronegative atom would have a greater pull on the electrons. Because remember, electronegativity is a measure of an atom's ability to attract electrons. Now, you can recognize nonpolar covalent bonds because usually these are bonds between the same type of atom, like a bond between two bromine atoms. Usually, a polar covalent bond is a bond between two different atoms. Now, a polar covalent bond is said to have a dipole moment, which means that one atom has a greater pull on electrons. Now, since that atom is pulling on electrons a little bit more, that atom would have a partially negative charge. So, here's an example of HF. Now, fluorine is more electronegative than hydrogen, so the dipole moment would be going in the direction of fluorine. Fluorine would have a greater pull on the electrons. So we would see that fluorine has a partial negative charge and hydrogen has a partial positive charge. And that's the symbol that we use to represent partial. Now in water, there's two dipole moments. Oxygen's more electronegative than hydrogen. So oxygen would get a partially negative charge and each hydrogen would have partially positive charges. Now when we look at electronegativities, you can see that for the most part, different atoms have different electronegativities, but there are a few cases where different atoms have the same electronegativity. So for example, phosphorus and hydrogen have the same electronegativity, so technically they'd make a nonpolar bond. Carbon and sulfur have the same electronegativity. Okay, so whenever you're given electronegativity values, you should always check and make sure that the atoms really do have different electronegativities. Because if they have the same electronegativity, then it would be a nonpolar bond. All right, so I want you to identify each of these bonds as polar or nonpolar. Pause, and then you can press play to check your answers. All right, so HCl is polar. Again, it's two different elements that have different electronegativities. The hydrogen-hydrogen bond is nonpolar because the same elements, they have the same electronegativities. Same situation with the bromine-bromine bond, and oxygen-fluorine is again polar because it's two atoms with two different electronegativities. Now, we talked about looking at each individual bond to figure out if the bond is polar. But then we have to look at the molecule as a whole because many molecules contain more than one bond. So to figure out if a molecule is polar, we're going to look at the bonds and see how they interact. Now, if the molecule has nonpolar bonds, it's automatically nonpolar. However, molecules with polar bonds are sometimes polar overall and sometimes nonpolar overall. A molecule can have polar bonds but be nonpolar overall if the bond dipole moments cancel out. So let's look at a couple examples. Water and carbon dioxide. Now in water, you can see that while those dipole moments are pointing in opposite directions, they both have a net upward pull. Whereas in carbon dioxide, they're pulling in exactly opposite directions with equal force. So in carbon dioxide, those dipole moments cancel out, but in water, they do not. So to summarize, if the bonds in a molecule are nonpolar, the molecule overall must be nonpolar as well. However, if the bonds are polar, the molecule itself can be polar or nonpolar, depending on whether or not the dipole moments cancel out. Now, if you've learned about vector addition in math, it's a little bit easier to understand, but we can also kind of shortcut figuring out whether the dipole moments cancel out or not. So there are certain shapes, we learned about the molecular geometries last unit, there are certain shapes that are always nonpolar if all the atoms around the central atom are the same. So the shapes are linear with 3 atoms, trigonal planar, and tetrahedral. So thinking about what all of these shapes have in common, you might notice that they have no lone pair of electrons on the central atom. So what that means is that these shapes are completely symmetrical, and so all the bond dipole moments can cancel out. Now it's important to note that this is not true if we have different atoms around the central atom. So for example, CH4 is nonpolar, but CH3Cl would be polar because not all of those 4 bonds around carbon are exactly the same. So then the following shapes can be polar, bent, and trigonal pyramid. And these molecules are polar if and only if the bonds are polar. So because they have that lone pair on the central atom, it makes them a little bit asymmetrical, and so the dipole moments do not cancel out. Now, if the bonds are nonpolar, the molecule will still be nonpolar because there were no dipole moments to cancel out in the first place. All right, so just to sort of summarize this, take a moment and pause and try to draw these Lewis dot structures and see if you can identify their shape, bond polarity, and molecule polarity. We'll do water together. So this is water's Lewis dot structure, and we know the shape is bent because water has 2 bonds around the central atom and 2 lone pairs. The bonds are polar because they're bonds between 2 different atoms with different electronegativities. And the molecule itself is also polar because those dipole moments do not cancel out. And our clue that they don't cancel out is that there are lone pairs in the central atom. All right, so pause and try to fill out the table for the other 3 molecules, and then press play when you're ready to check your results. All right, so for CO2, it is a linear molecule. The bonds are polar, but those dipole moments cancel out, so it's nonpolar overall. Ammonia is trigonal pyramid, polar bonds because they're different atoms, polar overall. And carbon tetrachloride is a tetrahedral. The bonds are polar because they're between different atoms with different electronegativities, but the molecule is overall nonpolar because those dipole moments cancel out. And again, the clue you can use for molecule polarity is to look at the central atom and see if there's a lone pair. That's not the reason why it's nonpolar, but that's your clue that it's nonpolar. All right, so try one more. Draw the molecule for H2S dihydrogen sulfide to determine its shape, then determine whether the bonds are polar or nonpolar, and the molecule, and press play when you're ready to check. All right, so this is H2S, it's bent, and the bonds are polar because sulfur and hydrogen have different electronegativity values, and the molecule is overall polar because the dipole moments do not cancel out. All right, so the whole reason that we care about molecule polarity is that it helps us determine the intermolecular forces between molecules. So intermolecular forces are forces that exist between molecules that hold them together. So if a molecule has strong intermolecular forces, the molecules stick together more. If it has weak intermolecular forces, the molecules are easily separated. So there's 3 types of intermolecular forces, dipole, dipole, hydrogen, and dispersion, but we're going to compare them to ionic forces too, since those also hold substances together. All right, so when we talk about these, we know that ionic forces exist when I have a metal and a nonmetal. And we don't really talk about the molecule polarity, it's just ionic. There's no individual molecules. Now, when we have polar molecules, we either have dipole-dipole forces or we have hydrogen bonding. Dipole-dipole forces exist when I have a polar molecule that does not have hydrogen bonded to nitrogen, oxygen, or fluorine. So hydrogen bonding is like a special type of dipole-dipole force when I have hydrogen bonded to nitrogen, oxygen, or fluorine, and it's a particularly strong interaction. And dispersion forces exist in nonpolar molecules. So again, we'll recognize those when we have that nonpolar molecule with no lone pair on the central atom. Now, when we compare the strength, it's really helpful to think about charge. So ionic compounds are really, really strong because they're held together by these full opposite charges. Like if you have sodium chloride, sodium is +1, chlorine is -1, and that's a very strong attraction. Now, hydrogen bonding is the next strongest because remember, these polar molecules have partial charges on the atom. So hydrogen bonded molecules have fairly strong partial charges. Dipole-dipole forces are a little bit weaker because they're held together with weaker partial charges. And dispersion forces are the weakest because when we have nonpolar molecules, they have no permanent partial charges on them. So there's no charge holding them together at all. All right, so what do you think has a higher boiling point? A molecule with strong intermolecular forces or a molecule with weak intermolecular forces? The stronger the intermolecular forces, the higher the boiling point. If I have strong forces holding molecules together, that means that it's going to take more energy to separate the molecules, making the boiling points higher. All right, so let's think about how intermolecular forces affect properties. So as intermolecular force strength increases, so does the boiling and melting point, because again, it takes more energy to separate these molecules. Molecules with similar polarities will be soluble or miscible. We call this rule like dissolves like. So you've seen this in real life. You know, for example, that oil and water don't mix. And that's because oil is nonpolar and water is polar. Now, we also know that larger molecules have stronger intermolecular forces. And this is because all molecules have dispersion forces in them, which are additive. That means that more forces means that it's stronger. So the larger a molecule is, the more places it has for these dispersion forces to occur. Now, this brings us to understanding why octane, which is the gasoline that you put in your car, is a liquid, while propane, which we use on a gas grill, is a gas. And this is because octane is a larger molecule. It has 8 carbons as opposed to 3. So since it's a larger molecule, it has more dispersion forces and therefore stronger IMFs. All right, so we know that the addition of a functional group can change the properties. So when we look at ethane, ethanol, and ethanoic acid and try to think about which has the strongest intermolecular forces, it winds up being ethanoic acid. So it has hydrogen bonding that occurs when we have the OH over here. Ethanol has hydrogen bonding as well. But it also has this dipole-dipole interaction with the carbonyl group, the carbon and the oxygen. Ethane would have the weakest intermolecular forces because it's a completely non-polar molecule, so it would only have dispersion forces. Now, intermolecular forces can also affect something called vapor pressure. So vapor pressure is the pressure that's caused by the natural evaporation of liquids, and you know that some liquids evaporate more easily than others. A substance with stronger intermolecular forces will have a lower vapor pressure. Let's think about why that makes sense. If the intermolecular forces are stronger, that means that the molecules are held together really tightly, so not as many of them will evaporate, escaping into the gas phase. Now, as the temperature increases, the vapor pressure will also increase. So as the temperature increases, molecules get more energy, and so more of them can escape into the gas phase. Now, an interesting fact is that liquids boil when vapor pressure is equal to atmospheric pressure. So I can actually use a vapor pressure graph to determine a substance's boiling point at standard atmospheric pressure, or really at any pressure. So if a substance boils when its vapor pressure is equal to atmospheric pressure, can we boil water at any temperature? The answer is yes, if the pressure is low enough. So you might have seen a video, and we'll look at one in class, where you boil water in a vacuum at room temperature. All you have to do is reduce the pressure enough that it's equal to the vapor pressure of water. All right, so let's look at this graph and take a minute to just sort of examine it. On the y-axis, we have the vapor pressure in kilopascals, which is a unit of pressure. And on the x-axis, we have the temperature in degrees Celsius. That dotted line at 101.3 kilopascals is standard atmospheric pressure. So when we're looking at this and trying to determine which substance has the strongest intermolecular forces, it would be the one that has the lowest vapor pressure at any given temperature or the highest boiling point. So this would be ethanoic acid. Now, the normal boiling point of ethanol at 101.3 kilopascal, let's look at how we'd figure that out. So we would draw a line from where ethanol meets the 101.3 line down to the x-axis, and we would see that it's roughly 80 degrees Celsius. Now, if we want to figure out what atmospheric pressure is required for water to boil at 75 degrees Celsius, we have to figure that out a different way. So we would start by looking at 75 degrees Celsius on the x-axis and drawing a line up to water. And then from there, we would look over to the y-axis. And the atmospheric pressure for water to boil at 75 degrees Celsius would be roughly 38 kilopascals. So if we lowered the pressure inside a vacuum chamber or something to 38 kilopascals, then water would boil at 75 degrees Celsius. And again, we can boil water at any temperature if we lower the pressure enough. All right, this is a lot to digest, so I recommend that you try the practice and ask a lot of questions if you're feeling stuck, and come see me for extra help if you need it.